Hey guys, welcome to CakeWalk Cambridge. I'm Aisha and you're watching Chapter 2 of IGCSE Chemistry Part 1 of Atoms, Elements and Compounds. So I've decided to divide this chapter into two because the first half is quite easy and it has all the basics, but if you don't get the basics right, you're not going to get the really important stuff later, right? So I thought we'll focus just on this first and then we'll go on to Part 2. So let's get started. Okay, so first we're going to properly define what atoms, molecules, compounds, mixtures, and elements are. Okay, so if you look here, you see atoms. Okay, we've all learned that atoms and molecules are particles that we've learned in chemistry already. Okay, so basically, an atom is a single particle, as you can see here. Okay, and atoms, when they come together, they form molecules. So two or more atoms bonded together form molecules, as you can see here. There are two atoms in each molecule, correct? Okay, so if you look at oxygen, for example, supposing this is an atom of oxygen, how exactly do we know oxygen? We know oxygen is written as O2, which means oxygen exists as diatomic molecules. Di means two, atomic means made of atoms, and diatomic molecule will mean this is an atom of oxygen, this will be a molecule of oxygen. Okay, that's pretty much what it means. Then we're going to go into compounds. So a compound is made from two elements that are bonded together in fixed proportions. Okay, so now basically this is an atom, this is a molecule. Let's say these are molecules of oxygen. Okay, oxygen is an element. So elements are substances made up of only one type of atom. Okay, only one type of atom. So if you're going to look at the element, let's take a common one, carbon. Carbon will only be made of carbon atoms. Let's say this is a carbon atom. If you look at calcium, calcium will only be made of calcium atoms. Okay, so that's its element. So this is one element, which is yellow as you can see, and this is another element. Each element has atoms that have their own properties and everything, own specific atomic mass and radius and everything. So basically everything is different. Okay, every element has some unique properties, and because they have their own unique properties, it means that they are made up of a unique set of atoms that is only for them. Okay, and then you can see there are some elements like oxygen that exist as molecules. So for them we will have like O2. So that'll have two atoms bonded together. Okay, so it depends on how the element exists. Okay, so that's an atom, an element, atom and molecules, they make elements. Okay, a compound is made by two or more elements, okay, that are bonded together in fixed proportions. Here you can see in this compound you have one big blue atom bonded to two small orange atoms. Another one big blue atom bonded to two small orange atoms. The same for the third. As you can see, it's in a fixed proportion of one blue. Okay, I'll write it probably in blue. So one blue is to two orange. It's a fixed proportion and that's never going to change. It's a compound. Okay, so a compound is like formed when elements are bonded together in fixed proportions, two or more elements. So if you're going to look, let's take an easy example. I'm just going to take all of this off firstly. Another 2:1 ratio. We're going to look at carbon dioxide. Okay. So when your first clue in how in the composition of the compound is in its name. Okay, we're going to look at carbon dioxide. Okay, the first clue is that there is carbon. Okay, over here. That's your first element, and your second element has to be oxygen because there's oxide. Okay, so we know that there is carbon and there is oxygen. And how do we know how much of each there is? So carbon is just one because it doesn't have a prefix or a suffix. Okay, it doesn't have a prefix. Usually the prefix di, as you can see over here, means two, as I already told you. So carbon dioxide means but there's one of carbon. Just gonna write it down. So carbon is gonna have there's gonna be one atom of carbon, and of oxygen there's gonna be two. Okay. So how are we gonna write it? You know the chemical symbol. So carbon is just C. So that's C. Oxygen is O. And because there's two of oxygen, the number of atoms will always go down as subscript over here. CO2. That's what carbon dioxide actually means. So if we had to draw it out, we can use the example over here. This can be an atom of carbon. Another color. This can be an atom of carbon. This can be oxygen. This can also be oxygen. CO2. This is carbon. This is oxygen. And this is oxygen. Okay. Same for the third. Okay. Um, so now I'm gonna give you just a little list of how you can use this. So di is used for two. Then the prefix tri is used for three. Mono is used for one. Okay. So if we have another element that is carbon monoxide, there's one carbon, there is oxygen, and it says monoxide, which means there's one oxygen. Okay. Whatever element that the prefix is attached to, that is the number. It is like the number that it is stating for the element that it is attached to. So if you're gonna say dihydrogen monoxide, that means dihydrogen. So two hydrogen, monoxide, one water. That's H2O, which is water. Sorry, two hydrogen, one oxygen. So H2O, that's water. Okay, that's basically how you remember it. So there's di, mono, and tri. Mono is one, di is two, tri is three. Okay. And if you want, so usually there are suffixes also, but the suffix is not usually for the number of atoms. Suffix is for the element, as you can see here. Use a different color. Oxide is for oxygen. If we had nitrate, what does that mean? Is it nitrogen or what? Because the 8. So basically 8, okay, usually means that there is oxygen attached to it, okay. 8 is used for oxygen attached to the element, okay. So nit means nitrogen is there. 8 means that there is oxygen. If it was nitrite, IDE, IDE means there is no oxygen and there is only nitrogen, okay. Then if you have sulfate, it means there is sulfur attached to it and oxygen. If it was sulfide, there is just sulfur. If you had chloride, just chlorine. But if you had chlorate, there's chlorine and oxygen, okay. So that's basically how you remember it. So 8 means there is oxygen, ide means there is no oxygen, mono means one, di means two atoms. Mono means one atom, di means two atoms, tri means three atoms, and if you have poly, it usually means 5 or more than like 3, basically, okay? But usually poly is for 5 plus. So, but you don't really have that in your syllabus. We're just going to focus on these and then you're good to go, okay? And the last part of this is mixture. A mixture is basically when there are two or more elements mixed together. So now in a compound, they are mixed together and bonded. Okay, they are all bonded in a fixed ratio. As you can see, every blue atom is bonded to two orange atoms. But in a mixture, the elements are mixed together disproportionately. So as you can see here, okay, there are three, okay, there are three different, so there's one compound here because it's bonded in a fixed proportion. One blue is to two orange. Then there is one element, let's call this, okay, so let's say the orange is oxygen, the blue is carbon. Okay, so this is carbon, and these are oxygen molecules plus O2. That means this is CO2, right? CO2. So we have one molecule of carbon dioxide, we have two atoms of carbon, and we have two molecules of oxygen. And they're mixed together, but none of these three distinct substances are bonded together. The carbon dioxide is not bonded to extra carbon or extra oxygen. The carbon is not bonded to carbon dioxide or oxygen. The oxygen is bonded to neither of the other two, which means it's a mixture. They are mixed together disproportionately, okay, and they are not bonded together, okay. That's basically what you need to know about mixtures, and I'm going to go ahead now because I've spent a lot of time on this slide. If you have questions, please email me or put in the comments. Okay, so now we're going to look at an atom. What is an atom? So an atom basically is a building block. It is the smallest unit of an element. Okay, it is so basically millions of atoms make up an element. So if I'm going to look at this calculator, it's made up of a million tiny atoms. Okay, that are all like bonded together and make up this calculator. We are made of atoms. Everything is made up of atoms. Okay, they are like the base, like the smallest building block of anything. Okay, so what an atom? So basically there was like a theory that said that the atom is the smallest particle or whatever that makes up the universe. But then we find out that atoms are also made up of subparticles. So we're going to look into that now. Okay, so an atom has a central nucleus that contains neutrons and protons surrounded by electrons and shells. So this is the center of an atom, this little part, and this center, this core, is called the nucleus. The nucleus comprises neutrons and protons. So their names give it away. Neutrons are neutral, no charge. Protons, pro. They have a positive charge. Okay, and around this nucleus there are different shells and orbitals. Okay, we're going to stick to the word shells. So we have different shells around the nucleus, and these shells contain electrons that keep spinning and rotating, that keep spinning on axis in these shells. Okay, so we can consider an atom to basically be like the universe. Okay, we're going to look at that analogy. The center, the nucleus of the atom is the sun of the universe, and the sun is surrounded by orbits, and on these orbits we have different planets. So on these shells we have different electrons. Okay, that's basically what it is. This is a carbon atom, very basic, very important. So electrons orbit the atom, they're negatively charged. Protons and neutrons remain in the nucleus bonded together. Okay, so now if you're going to look here, electrons are negatively charged. Okay, and protons are positively charged, neutrons have no charge. But if you look at this is not charged. This substance is not charged. Like everything is made up of atoms, but they're not charged, like they're neutral substances. Why is that so? Because the number of protons in the nucleus of an atom equal the number of electrons that orbit the nucleus in the shells. And plus and minus always cancel out, right? So basically, if we have six positive protons in the nucleus and we have six negative electrons in the shells, I'm going to do the math here. Plus 6 in the nucleus minus 6 in the shells equal to 0. That's the overall charge. It's neutral. And then we also have neutrons, but the neutrons also have a 0 charge. So 0 plus 1, 2, 3, 4, 5, 6. There are 6 neutrons. So 0 plus 6 into 0 gives you 0. So the overall charge of an atom is 0 and it is neutrally charged. It's neutral. It doesn't have a charge. Okay? That's basically what an atom is. Yeah, protons are positively charged, neutrons are neutral, and electrons are negatively charged. Okay, so the charge of a proton is +1. This table is extremely important. It's like an easy 2-3 marks. Okay, proton is +1, neutron is 0, electron is -1. Now you'll also need to know the mass of a proton. So we use the mass of a proton is basically just 1. Okay, the mass of a neutron is also 1. So protons and neutrons have the same mass, okay, but the mass of an electron is 1 by around 1840, or check your textbooks for an updated number, but as far as I knew it was 1 by 1840, which is basically nothing. It has a negligible mass, like it's literally nothing. Like if you put this on like a calculator or something, it'll give you like, let me try and see what comes. It's 5.4 into 10 raised to -4, which is like 0.0005, which is like hardly anything. Okay, so proton is +1, and the charge of an electron is -1. The neutron is neutrally charged, it's got a charge of 0, but protons and neutrons have the same mass, and electrons have a negligible mass or 1 by 1840. I think you can write either, but check with your teacher. Okay, and it's very important to remember the charge and the masses. Okay, remember protons and neutrons, same mass. Protons and neutrons in the nucleus, protons and neutrons, same mass. Okay, that's what you need to remember. So now we're going to do some basic definitions. What is the proton number of an element? Okay, or an atom. Okay, so the proton number is basically the number of protons in the nucleus of an atom. So if we're going to look at carbon, we just did that, it had 6 protons in the nucleus. Okay, so the proton number of carbon is 6. Okay, also if we like another synonymous term for proton number is atomic number. So the atomic number of carbon is 6. Okay, now also the atomic number or proton number is basically the order of the elements when you memorize them, or if you've gone through the periodic table song, it's hydrogen and helium, lithium, beryllium. So it goes on like in order. So hydrogen is 1, helium is 2, lithium is 3, beryllium is 4, boron is 5, carbon is 6, as you can see. So basically elements have been arranged in the periodic table, okay, which is like a table. I think you've done that before. So elements have been arranged in the periodic table according to proton number, an increasing number of proton number. So you will always learn them like 1, 2, 3, 4, 5, 6, hydrogen, helium, lithium, beryllium, boron, carbon. Okay, it's always like that. So the proton number is the number of protons in the nucleus of an atom. 2 keywords, number of protons, nucleus of an atom, could come for an easy 2 marks, and most people lose the second mark in the last part. Nucleus of an atom. Then we have the nucleon number or the atomic mass. Okay, now why is it called? Yeah, so basically the nucleon number. We'll first focus on the first easy part. So nucleon number is the number of protons and neutrons in the nucleus of an atom. As you can see, nucleon number, it gives away that it's going to give you the number of particles in the nucleus of the atom. Now in the nucleus of the atom, you only have 2 types of particles, protons and neutrons. So that means it's going to add up these 2 numbers and give you the whole number. And whatever particle is found in the nucleus of an atom is called a nucleon. So a proton is a nucleon, a neutron is a nucleon. And the nucleon number will be the total number of nucleons, which is the total number of protons and neutrons, again, in the nucleus of an atom. Now, another important thing is that nucleon number is synonymous with atomic mass. Okay, so basically, why is it synonymous with atomic mass? It is synonymous because the mass of an atom will only come from its protons and neutrons. Electrons, as we discussed earlier, have a negligible mass of 1 by 1840. It's a negligible mass, means we don't count it. Okay, that means the mass of an atom will only come from the nucleon number, from the protons and neutrons, which is why nucleon number and atomic mass are synonymous. So in carbon, in the nucleus, we had 6 protons and 6 neutrons. Now we learn, so 6p plus 6n is equal to the atomic mass. Okay, now what we need to do is we need to find out the mass. How will we do that? 6 into p. The mass of p is 1 plus 6 into n, which is also 1. 6 into 1 plus 6 into 1 is 6 plus 6, which is 12. So basically, instead of doing the into 1 thing, I'm just doing it like to make it simple for you to understand. You just add up the number of protons and neutrons in the nucleus of an atom, and that gives you your atomic mass or nucleon number. Remember, atomic number is protons, just protons in the nucleus of an atom. Atomic mass is protons and neutrons in the nucleus of an atom. Very important definitions, that's why separate slide for them. Okay, so now electronic configuration. So basically, as we discussed, electrons orbit the nucleus in shells. Okay, so each shell has a designated number of electrons that it can hold. So each shell, so like let's say this is the nucleus of an atom. This is shell number 1. This is shell number 2. This is shell number 3. Okay, so each shell 1, 2, and 3 can hold a specific number of electrons and not more than that number. Okay, they can never hold more than that number. Now, how do we know which shell number can hold how many electrons? There is a formula. which is 2n square. Okay, now what is n? N is basically the shell number. So we're looking at shell number 1. The number of electrons it can hold is 2n square. So for 1, it's equal to 2 into 1 square, which is equal to 2 into 1, which is equal to 2. So the first shell can hold a maximum of 2 electrons. The second shell can hold 2 into 2 square, which is 2 into 4, which is 8, maximum of 8 electrons. Third shell, 2 into 3 square, which is equal to 2 into 9, maximum of 18 electrons, and it goes on and on and on. Okay, so your maximum number of electrons that any shell can hold is 2n square, where n is the shell number. Okay, but now there is another little criteria that has to be met. The last shell of an atom cannot hold more than 8 electrons. So let's say that you have okay, let's look at lead. The electronic configuration of lead is 2. That's 2 in the first, 2 electrons in the first shell. 8, 18, 32, 18, and 4. Okay, now if you look here, the first shell is holding its maximum capacity, the second shell is holding its maximum capacity, third shell maximum capacity, fourth shell is also holding its maximum capacity. So the fifth shell's actual maximum capacity is 2 into 5 square, correct? Which is 2 into 25, which is 50. So ideally, it should be able to hold 18 plus 4, which is 22 electrons. But then the last shell, that means the last shell here would be the fifth shell, and that would hold more than 8. 22 is greater than 8. Therefore, it is split, and 18 electrons are held in the fifth shell and 4 in the last shell. Okay, so the last shell cannot hold more than 8 electrons. Okay, that's important. Now, why? Because there are 8 groups in the periodic table. Okay, groups are basically columns. Okay, vertical columns. There are 8 of them. Okay, and the last shell holds a certain number of electrons, correct? And the number of electrons held in the last shell indicate the group number, which is why there cannot be more than 8. It's very fascinating. So let's say lithium. Okay, lithium. So lithium is basically proton number 3. Proton number 3 is lithium, which means it has 3 protons in the nucleus of an atom of lithium. So the electronic configuration would be 2 in the first shell, correct? Because 2n square, so it can hold 2. Comma, how many electrons are left? 3 minus 2 already done, so 1. Does it satisfy the criteria of less than 8 electrons being held in the last shell? Yes. Okay. And so basically it's 2 comma 1. Now the last shell has 1 electron. The last shell also indicates the group number. Last shell has 1 electron, therefore it's in group number 1. Okay. So that's basically what it means. Therefore, because of this, noble gases, which is group 8, will have a full outer shell of electrons, which means that the last shell of electrons will always have 8 electrons. Because the group number is dictated by the number of electrons in the last shell, group 8 noble gases will have 8 electrons in the last shell, and 8 electrons in the last shell means it has a full outer shell of electrons. Okay, already spoken to you about this point. And then we have number of electron shells. So the number of electrons in the last shell indicates the group number, and the number of shells indicates the period number. Period is basically the horizontal rows. Okay, they go like this in the periodic table. So we look at lead, it's 2, 8, 18, 32, 18, 4. So it should be in period number 6. I'm going to count at the periodic table above me. So that's 1, 2, 3, 5, 6. And yes, there it is. It's in period number 6. Okay. So number of electron shells is an indicator of the period number. Okay. And there we go again. Number of protons in the nucleus is equal to number of electrons in shells for neutral atoms, because they have to have a neutral charge. Plus and minus have to cancel out. Okay. I hope this is clear. You can email me if you have any other questions. Okay, so this is basically the periodic table. I thought this was really important to do. So these are groups 1, 2, And then we have 13, 14, 15, 16, 17, 18. So here you can see there's 3, 4, 5, 6, 7, but usually this block of elements is transition elements as you've learned earlier. So we're not going to count that. Okay, so this is group 1, this is group 2. And as you can see here, it's group 13. So we're going to just look at the last digit. So group 3, group 4, group 5, group 6, group 7, and group 8. Okay, that's how we look at it. Periods, horizontal rows. So that's period number 1, period number 2, 3, 4, 5, 6, 7. Okay. Basically here the 1, 2, as you can see the elements are arranged in increasing proton number. So 1, 2, 3, 4, 5, 6, 7. This is all proton number. Okay. If you can see it increasing by 1, 1 each time, it's proton number. That's basically what you need to know for now. We're going to look at electronic configuration now. I've done a lot of work for this part to explain it to you properly in case you didn't pay attention in grade 8. So yeah. So hydrogen. So basically hydrogen has a proton number of 1, which means that the number of protons in the nucleus is 1. Right. Nucleus, and you see number of protons is 1 proton. But then if you look, the mass number is also 1. But the mass number, as we discussed, mass is equal to protons plus neutrons. So if the mass number is 1 and the proton number is 1, neutrons has to be 1 minus 1, which is equal to 0. So there are no neutrons in the nucleus of a hydrogen 1 atom. Okay. Here you can see here the number of neutrons is equal to mass number, atomic mass minus atomic number, or nuclear number minus proton number, whichever synonymous terms. 1 minus 1, 0. So the electronic configuration is just 1. That means there is only one shell in hydrogen, and that one shell will contain only one electron. That does satisfy both the criteria that shell number 1 can carry a maximum of 2 electrons, and the last shell, which is also the first shell in this case, has to have less than 8 electrons. 1 is less than 2, 1 is less than 8, it is satisfied. Okay, that's how we know. Next element, helium. So now the top usually indicates the mass number, which is the protons plus neutrons, and the bottom here usually indicates just the atomic number, which is just the proton number. So you can see the proton number is 2, the mass number is 4. So that means the number of neutrons is 4 minus 2, which is 2, as indicated here. So I'm just explaining to you like everything about the configuration of the atom, not just electronic configuration, it's everything, just for you to understand. There are 2 protons, which means that there have to be 2 electrons as well. So the electronic configuration is just 2. It satisfies 2n square, and that the last shell has to have less than 8. Next, lithium. Lithium has an atomic mass of 7, which means there are totally 7 protons and neutrons. Totally, number of protons and neutrons equals 7 in the nucleus, and it has 3 protons. So the first indicator is if it has 3 protons, it's a neutral atom. So it has to have 3 electrons. And the second thing is number of neutrons is 7 minus 3, which is equal to 4. Okay, electronic configuration of electrons is basically 2 in the first shell. It cannot be 3 because 2n square. The maximum is already satisfied. So 2 comma and 1 is left over. So 2 comma 1. Okay. Next, beryllium. Atomic mass is 9. Atomic number is 4. Atomic number is 4. Therefore, there are 4 electrons as well. Okay. Number of neutrons is 9 minus 4, which is 5. Okay, number of neutrons is always the bigger number minus the smaller number by default. Okay, because the mass number is always going to be bigger or the same in the case of hydrogen 1. The electronic configuration, 4 electrons, 2 in the first shell. It cannot exceed 2. First can only have max 2. The leftover is 2. Okay, this also means that it is in the second group because it has 2 in the last shell. And it also means that it is in the second period because it has 2 shells. 2 comma 2 means 1 shell plus 1 shell, 2 shells. Next, boron, atomic mass 11, atomic number 5. Because atomic number is 5, there are 5 electrons. So it's 2 comma 3. 3 is left over. Mass number minus proton number will give you number of neutrons, which is 6. Okay. Carbon, already done this. I'm just going to go over this quickly now. So there are 6 atom, it's 6 protons, which means there are 6 electrons. So the configuration would be 2, 4. And please note here in the second shell, we are still sticking to less than 8 electrons in the last shell and less than, oh yeah, the second shell cannot have more than 8 electrons anyways because it's 2n squared, so 2 into 4. So less than 8 is our only criteria for the second shell. And the last shell, so 2, 4. Nitrogen, same 2, 5. We're just going to increase it by 1 each time. Oxygen. Okay, now we're going to do this a little slowly. So we have fluorine, which is 19 totally. So protons plus neutrons equal 19. Here we're given that protons is 9. So 9 plus n equals 19. Therefore, n is equal to 19 minus 9, which is 10. 10 neutrons. We know that there are 9 protons, therefore there are going to be 9 electrons. So it's 2, how many are left over? 9 minus 2, 7 electrons. Now here this is in the 7th group and this is still in the second period. Okay, then we have neon, 10. So now here the electronic configuration is 2, 8. Okay, and now this means it has a full outer shell of electrons because the last shell has 8 electrons, which also means it's a noble gas and is found in group 8. Now what happens when we go to atomic number 11? That means there are 11 electrons. So the first shell will have to have 2 because 2n squared dictates it will have to have 2. Now can the second shell have 9 because 2 and 9? No, because the second shell cannot hold a maximum, cannot hold more than 8, and the last shell anyways, which would have been this, cannot hold more than 8. So we do 2, 8, and what is left over? The balance is 1. 2, 8, 1. Now what does this mean? We have entered a new period, period number 3, because there are now 3. 1, 2, 3 electron shells, and this is group 1 because there's 1 electron in the last shell. Okay. Now that's all for that. Now we're going to go on to isotopy. So basically isotopes are atoms of the same element that have the same proton number. The proton number of an element will never change no matter what. Proton number remains the same. So isotopes are atoms of the same element that have the same proton number. Okay. Therefore, isotopic atoms will have the same number of electrons because proton number is same, electron number will also be same. Okay, they'll have same number of electrons, but the difference is that they have a different atomic mass. Now, atomic mass, okay, is made of protons and neutrons, correct? So now, if your mass is say 10 and protons is equal to 5, neutrons is 5. Now, if your mass is 11, protons have to be the same. Protons are always going to be the same. That's why elements are distinguished by their proton number, not by their mass number, because mass number can change. If they're still going to have 5 protons, how many neutrons will they have? 6. So therefore, isotopes are atoms of the same element that have the same number of protons, but different number of neutrons in the nucleus of an atom. Important definition, 3 marks. Okay. So they have a different nucleon number, which is caused by a different number of neutrons. Okay, and because they have the same proton number, they have the same number of electrons in the atom. Now, chemical activity in an atom is dictated by electronic configuration. That is the number of electrons in the last shell of an atom, and we'll see why in part 2. Because bonding, ionic bonding, covalent bonding, that's all dictated by electrons in the last shell. That's why a last shell is very important, okay? So now if you're going to have the same number of electrons in the atom, that means it will have the same electronic configuration, correct? Same number of electrons in the last shell also. So the chemical properties are unchanged, but the physical properties of isotopes are changed because they have a different mass number, they have a different density, different like different mass and different density. And those are the two most important things. Okay, so the physical properties are changed of isotopes, but the chemical properties remain the same. Okay, so if you look at hydrogen, I think there's an example later. Okay, I'll show you. Okay, I'm going to show you right now. So that's hydrogen 1, hydrogen 2, and hydrogen 3. That's hydrogen, deuterium, and tritium, I think. I'm not sure of the names yet. I think it's that. So basically, hydrogen 1 means it has a mass number of 1. proton number remains the same. So we're going to write hydrogen chemically. So proton number is the same, but it has a mass of 2. Here, proton number is the same, but it has a mass of 3. Number of neutrons here is 1 minus 1, 0. Number of neutrons here is 2 minus 1, which is 1. Number of neutrons here is 3 minus 1, which is 2. You see, all three of them have different masses, different neutron numbers, same proton numbers, same electron numbers, same chemical properties, different physical properties. Okay? So different atoms of the same element that have the same number of protons but different number of neutrons in the nucleus of an atom. This is your perfect definition. Don't mess it up. Okay, why is it black? This one. And then we have same chemical properties because same number of electrons, therefore same number of electrons in the outer shell, same electronic configuration. These are your standard answers that they ask you a lot in papers, so mug up this slide. Okay, now we're going to look at relative atomic mass. This is the last part of our video today. It's a really long video just for like 2.1, 2.2 and 2.3, but these were really important concepts. So basically relative atomic mass. So now when we have different isotopes that are present naturally in the environment, how can we find an average starting, like an average mass that we can use for basic calculations when we're using like different elements? Okay, so what we do is we find out their relative abundance. Relative abundance is how commonly present they are in the environment. So iron that has a mass of 54, Fe is ions. Iron that has a mass of 54 is present 5.95% in the environment. Iron that has a mass of 56 is present 91.88% in the environment, which is the largest. And iron which has a mass of 57 is present 2.17% in the environment. So now how we find out the relative atomic mass, that's the average atomic mass of the element. You basically multiply each mass, not the proton number, the atomic mass, each mass by the abundance. You add each of these and then you divide by 100. Okay, because 5.95 plus 91.88 plus 2.17 equals 100 because they have to equal 100%. The abundance has to equal 100% always. Okay, so because it's a percentage out of 100. So what you do is you multiply 54 into 5.95 plus 56 into 91.88 plus 57 into 2.17. Add each of these quantities, divide by 100 and you get your answer. Okay, so now I'm going to give you all an example, the next one. So we have chlorine 35 mass, which means that the proton number is the same. Okay, that is I think 17. Yeah, I think chlorine is 17. Yeah, so the proton number of chlorine is the same, but the mass number is different, which means it has a different number of neutrons. So what we are going to do is we're going to find out the relative atomic mass of chlorine. So what we're going to do is the mass number here is 35. So we're going to do 35. Okay, has 35 into the abundance here is 75%. So 35 into 75. I'm going to put brackets so you don't get confused about what to multiply. And then we add it to 37, the mass number, into the abundance, which is 25. And you divide this whole quantity by 100. I'm going to do the quick calculation. 35 into 75 plus 37 into 25 by 100. 35.5, which is the correct answer, which is also going to be given in your periodic table booklet in your exam, because that's the relative atomic mass. That's how you find it out. You multiply mass by abundance, add up all the quantities, divide by 100, you get your answer. So that was basically it for part 1 of this chapter. I hope it helped you and I hope you enjoyed learning this. I hope it wasn't too long. And if you have any questions, you can email me. And I also have an Instagram page. It's called CakeWalk Cambridge. And you can follow it for more concept revision for biochem and English. I've just started it with my best friend. And we're going to keep posting. And yeah, stay tuned for more. And please like this video if it helped you. Comment if you have any questions. And yeah, let's get through this together.